Dave, you can make a start.
Okay. Right, good evening, ladies and gentlemen. On behalf of the Lancashire panel of the Institute of Mechanical Engineers, I'd like to thank you for joining us this evening. We are very lucky to have this presentation given by Dr. Robert Ian Taylor, who is a very gifted and respected man, as you'll hear. Ian is a fellow of the Society of Tribologists and Lubrication Engineers and a fellow of the UK's Institute of Physics. He was awarded a Natural Sciences Physics degree by the University of Cambridge and a PhD in Applied Physics and Electronics at Durham University. From 88 to 91, he worked as a research scientist, mainly modelling semiconductors, waveguides and low noise transistors. And then in 1991, he joined Shell. Shell Research Limited, mainly modelling semiconductors, waveguides. Joined Shell Research Limited, predicting oil film thicknesses and friction of piston rings, journal bearings, and valve train systems, with the aim of building mathematical models through tribological activities. This made a valuable contribution to improved efficiency of passenger vehicles and Formula One development. He continued his career with Shell in various roles till 2020, when he retired, and he also was awarded the IMechE Tribology Silver Medal in 2020. At the same year, he was appointed visiting professor in lubricants at the University of Central Lancashire, and now he's also on the staff there, working alongside Ian Sherrington on various interesting projects. Ian has registered several patents. He's been extensively published. He's received several awards from the Society of Automotive Engineers. He's been the past chair of the IET. He serves as the editor on the Institute of Mechanical Engineers Proceedings Journal of Tribology. Without further ado, I would ask Ian to give his presentation, which I'm very much looking forward to, the energy efficiency and carbon dioxide emissions of electric vehicles.
Okay, thanks, Dave. I hope everyone can hear me. I'll move on to the slides. So yeah, I'm going to talk about the efficiency and carbon dioxide emissions of electric vehicles. And an overview of the presentation. I'm going to give spend a few minutes discussing why there is such a focus on decarbonising passenger cars, and then I'll move on to comparing how different consumer transport options compare against each other. So I'll look at conventional petrol cars, electric cars, hydrogen cars, and even a bicycle, and look at their energy efficiency, their CO2 emissions, the other emissions, and the cost of fuel. And then, because one of the purposes of moving to electric cars is to reduce CO2 emissions, we need to look at where the electricity is coming from, because although CO2 emissions will no longer be emitted from the tailpipe of an electric vehicle, the CO2 emissions will potentially be emitted from the power plant that makes the electricity. So it depends on what fuel you use to make electricity as to what the CO2 emissions are. In addition to CO2 emissions from driving, there are also CO2 emissions happen during the manufacture of the car. And so you also need to look at how much CO2 emissions are emitted during manufacture, and you've got to balance that over the lifetime of the vehicle, and that also has an impact on the CO2 emissions. Then I'm going to look at how the UK electricity supply, where the fuels for UK electricity have changed over the last 30 years. And finally, I'm going to talk a bit about heavier duty vehicles, so heavy duty trucks, ships and planes, and what the CO2 emissions are for them and what the options are for reducing CO2 emissions from them in the future as well. And hopefully there'll be plenty of time for discussion and questions and answers. So why is there such a big focus on decarbonising passenger cars? This figure below shows roughly where CO2 emissions come from for the average person in the developed world. So 35% of CO2 emissions come from transport, and that's cars, trucks, planes and ships. And of that 35%, road transport, that's mainly cars and buses, account for about half of that, so roughly 18%. And if you think about a car, it's very inefficient in terms of its utilization. If you only drive an hour a day in your car, you're only using that machine for 4% of the time. And the amount of energy used to drive for that hour is relatively low. And so having a battery to do that is actually quite a plausible and achievable option. And so you could immediately almost reduce 18% of your CO2 emissions from driving just by moving to an electric car. Obviously, it's not as simple as that, because you've got to make the batteries and you've got to get all the infrastructure right and the charging. But basically, it's a fairly low-hanging fruit in terms of reducing CO2 emissions. If we look at some of the other areas of CO2 emissions, we obviously have CO2 emissions from hot air, so that's mainly heating and gas. And although the UK government is looking at options for reducing CO2 emissions from heating, I mean, that's going to take 20, 30 years for people to move from, say, gas boilers to alternatives. And some of the other things on here are more minor. So lighting is an interesting one. The CO2 emissions from lighting has probably already decreased substantially in the last 20 or 30 years because people have moved to low emission light bulbs. So if we go back 30 or 40 years, people used to have 60 watt and 100 watt light bulbs in their house, and now most light bulbs are down about 10 watts. So there's been a big reduction in CO2 emissions from lighting from the move to low energy lighting. And just to put all of this into context, this is the sort of average figures from someone in the developed world. And if you look at these sort of figures, the average energy budget per person per day for the UK is around 125 kilowatt hours. So that's from things like driving, heating, lighting, everything. So that's a fairly substantial amount, and it's probably double that of people in less developed worlds, less developed countries. But I should say it's substantially less than the average in somewhere like the US. So Europe is sort of quite a lot more energy efficient than the US, but we're still we use a lot of energy compared to developed countries. So anyway, that's one of the reasons for the focus on cars. It's a fairly low-hanging fruit in terms of reducing CO2 emissions. I mean, it might still take 20 years to move everyone from current conventional cars to electric cars, but it's relatively short term and it'll have a relatively big impact. So that's why there's such a focus. Now the next slide is the key slide of the talk, really. I'm looking here at how much energy it costs to go 100 kilometers in different modes of transport. And so what we've got is on the top line of this table, how much energy is needed to travel 100 kilometers. And for an electric car, it's typically between 15 and 25 kilowatt hours. For a conventional petrol car, a fairly efficient modern car uses 6 litres of gasoline, and the energy content of that equates to about 57 kilowatt hours. If we look at a hydrogen car, we actually have to make hydrogen to fuel the car, and it takes about 50 kilowatt hours to make a kilogram of hydrogen by electrolysis, and that's the main method by which hydrogen is made today. And then finally, cycling. If you cycle 100 kilometers, it's a fairly low amount of energy, about just over 2 kilowatt hours. In fact, it's quite interesting where this estimate comes from. If you cycle at, say, 20 kilometers an hour, you're probably putting out about 100 watts of power. And so you would have 500 watt hours of energy for the 100 kilometer bike ride. But in fact, your body is only about 20% efficient at converting food to energy. So that 500 watt hours to push the bike at the pedals equates to over about 2 to 2.5 kilowatt hours of food that goes in to enable you to do that. And there's a book I will talk about later, David IMechE, Sustainable Energy book, where this figure of 2.2 kilowatt hours comes from. But if you work backwards from the power you need to cycle and take the efficiency of your body into account, I mean, that figure looks pretty good. So there's some quite interesting things to talk about in these figures. So and I should say that the numbers for the electric car and the conventional car, manufacturers, when they make the car, they have to drive the cars on a standard test drive cycle, and they actually have to report what the fuel consumption is for a petrol car. They have to say how many litres per 100 kilometres the petrol car will do on this standard driving cycle. And the electric cars drive on exactly the same cycle, and they have to report how many kilowatt hours are needed to drive that cycle. And so the manufacturers will list what the fuel consumption is on their website, and the figures should be available when you buy the car. And the reason there's a range for an electric car from 15 kilowatt hours to 25 is that the energy you need to go 100 kilometers depends on the mass of the vehicle. So if you have a heavier electric car, you'll be more likely up at 25 kilowatt hours, and if you have a lighter electric car, you'll be down at 15 kilowatt hours. So you might ask, why is there such a big difference in energy between an electric car and a conventional car? And the main reason really is that when you burn gasoline, most of the energy is lost straight away. So most petrol cars, 60% of the energy in the petrol is lost straight away as heat and noise. So that immediately brings you quite down from 57 kilowatts down to 40% of that value. And then you've also got losses in the engine and the transmission. And if you drive on the same driving cycle, the power you need at the wheel, whether it's an electric car or the conventional car, the power at the wheel will be exactly the same. It's just that in the case of the gasoline car, only 20% roughly of the 57 kilowatt hours gets to the wheel. Whereas in the case of an electric car, roughly 70 to 80% of the power in the battery can get to the wheel. So effectively, the electric car is just more efficient, which is why the actual energy is lower. Now, if we go on to the second line, we can estimate what the CO2 emissions are for these different modes of transport. And the UK government has figures on how much electricity, how much CO2 is emitted from the electricity mix in the UK per kilowatt hour, and you can sort of look up those figures. And so in the UK, we've got more than 50% of our electricity comes from low carbon sources, and those are mainly nuclear, wind and solar. And most of the rest comes from gas, which is a lower CO2 option than coal or oil. So in fact, the UK, we have quite a low CO2 emission mix for our electricity system. And for this 15 to 25 kilowatt hours, the CO2 emissions equate to only 4 kilograms. If we compare that to 6 litres of gasoline, a litre of gasoline emits about 2.3 kilograms of CO2. So that quickly, you can quickly do the calculation and you get 14 kilograms. For hydrogen, it's a bit more complicated because you've got to look into exactly how the hydrogen is made, and etc. And there's a link at the bottom of this slide which I used, and that came up with a figure of 9 kilograms of CO2 emissions to make the hydrogen you needed to go 100 kilometers. And then finally, somewhat surprisingly, you also get CO2 emissions from cycling, because if you look at the average person in the UK, every day, just by eating food, we emit about 8 kilograms of CO2. So I've assumed that if you cycle 100 kilometers, you eat an extra 25% of food than you would normally do, and that gives you your extra 2 kilograms. But in fact, this number does depend quite a lot on the diet. If you eat a lot of meat, the figure could actually be higher than 2 kilograms because the production of meat entails a lot of CO2 emissions. Then finally, if we look at the, well, not finally, but the next line down is the cost. And these figures are slightly out of date because when I put this slide together, it's a few months ago. But I've assumed an electricity price of 18 pence per kilowatt hour, which is the standard rate, I think, more or less, and a petrol price of £1.30 per litre. And so you end up with the electricity cost of between £3 and £4, £3 and £4.50 roughly, whereas a car would be about, petrol car would be about £8. A hydrogen is not easy to get hold of in the UK. There's only about 3 or 4 sites around the world, around the UK, and it's about between 10 and 15 pounds a kilogram for hydrogen if you can find one. And then finally, even for cycling, if you have to eat extra food, that's going to cost you some money as well. And then refueling time, I mean, this is where the disadvantage comes from an electric car. You are obviously going to take longer to refuel the battery, to charge the battery up, and it could be 20 minutes up to a few hours depending on how big the charger is that you plug into. And this compares to sort of maybe 5 minutes for conventional cars and hydrogen cars. But obviously if you cycle 100 kilometers, you're going to take quite a while to recover from that. And then finally on this graph, we look at the other emissions. Now for the electric car, there's no tailpipe emissions at all. For a petrol car, you've got both nitrogen oxides and particulate matter, and these will impact local air quality. For hydrogen, there's not really any tailpipe emissions apart from water, and there's not any real emissions from cycling either. But I mean, this is an important point. Although in the UK, we're talking about moving to electric cars to reduce CO2 emissions, in other countries such as China, the motivation for electric cars may be more to do with local air quality than CO2 emissions. So if you're in a large city like Shanghai or Beijing, the fact you can remove your NOx and particulate matter from all these car tailpipes, that might be more of a motivation to move to electric cars than CO2 emissions. So in China, for example, they have lots of coal-fired electric power stations, and you could say, well, the CO2 emissions from coal make the use of an electric car not very sensible. But in fact, if they're interested in the local emissions, that is the other reason for why they would move there. So this table is actually quite instructive as telling us why there's so much interest in electric cars. And basically it's because you don't need much energy to go 100 kilometers in an electric car because the efficiency is better than a conventional car. And secondly, if you have a electricity system which is relatively low carbon, you can drastically reduce your CO2 emissions. And the other benefit for customers, of course, is that it will actually cost them less to recharge their car to go 100 kilometers with electricity than it will to fuel the car with conventional fuels. So I've talked about electric cars. Sorry. Like I say, the CO2 emissions have been moved from the tailpipe of the vehicle to the power station. And so the amount of CO2 at the power station depends on how the electricity is generated. And this slide, again, this is from UK government official figures, and there's a link at the bottom that you can have a look at. So if you generate the electricity from coal, the CO2 emissions for 100 kilometers of travel by an electric car would be actually about almost 15 kilograms. So in fact, if your electricity comes from coal, your emissions could actually be higher than from the gasoline car, which is shown at the right hand side. If you've got natural electricity generated from natural gas, that's still a fossil fuel, but the emissions are quite a lot lower than from coal. It comes down from about 15 kilograms down to just over 8. And then if you've got solar, nuclear and wind, there's a substantial reduction down to about a kilogram or less. There are still numbers for these types of electricity because you've still got to make the solar installation or the nuclear power plant or the wind turbines, and that will have a CO2 footprint, and you've still got to run them. So they're not zero, but they're substantially lower than for natural gas or coal. And then from the new 2019 government figures, the electricity from the UK mix of how electricity is generated came in at just under 4 kilograms, which is where I got the figure from in the previous slide. So if we are in a country where you've got lots of coal, you're probably no better off in terms of CO2 emissions than you are with a conventional petrol car. But if you're in a country like the UK where we've decarbonised our electricity system to quite a large extent, we can go from almost 14 kilograms for the gasoline car on the right hand side down to 4. So there's a reduction, reduction of about 2/3. So that's not the whole story, because the manufacturer of a car also takes energy, and you need to account for the CO2 emissions generated during the manufacture of the car. And there are a couple of references here where people have tried to do this. And what they find usually is that for a conventional car, shown on the left-hand side, the manufacturer of the car, if you average the manufacturing costs over 200,000 kilometers, which is the lifetime of the car, they come in about 25 grams per kilometer. Whereas an electric car, again, if you average the manufactured cost of the electric car over the lifetime, which again is assumed to be 200,000 kilometers, you get about 50 grams per kilometer. So when you add that on to the amount of CO2 emissions from electricity generation, you can then compare directly the conventional car with the electric car. And as I showed before, if you've got coal, you're coming out at slightly higher than the conventional car, even taking into account the manufacturing costs. Whereas if you move to gas, there's a fairly substantial reduction. And if you move to solar or nuclear, you've got a pretty big reduction, almost a quarter. So these are from the reference at the bottom. I mean, the one thing I would say is that the manufacturer costs are averaged over the lifetime of the car. So if you buy an electric car and only keep it for 10 years and only drive 5,000 miles a year, the CO2 emissions would actually be higher. So it is arguable you could end up being better buying a conventional car if you're only going to do short distances and not drive the car very much, or you might even be better just using public transport. But I mean, it's important to take into account the manufacturer of the vehicle and those CO2 emissions and average those over the lifetime of the car to get a full picture of what's going on. So I've said a bit about electric cars and their benefits. You clearly need to have a low carbon mix of electricity to get the benefit in terms of CO2 reductions from an electric car. Now this graph shows two things. On the right hand side, data from 2018 and 2017 shows where the electricity came from in the UK. And in 2018, I think that was the first year that more than 50% of UK electricity was from low carbon sources. So the figure on the right hand side, renewables, which is wind and solar primarily, was 33.3 and nuclear was 19.5. So that came in at 52.8%, and most of the rest was gas, which came in at about 40%. And gas is it's still a fossil fuel, but it's a lower carbon option than coal or oil. So that is one reason why the UK electricity system has a relatively low CO2 footprint. The second thing to point out, on the left-hand side, this is a graph of the electricity demand, if you like, in the UK over a year. And a lot of people talk about electric cars. They worry about whether there's enough electricity to suddenly charge up all these electric cars. What's interesting here was the peak demand in the UK actually happened around 2005, and there was about 380,000 gigawatt hours of electricity supplied that year. And since then, electricity has been dropping quite a bit, the demand. And I think there's a few reasons for this. Lighting could well be one of them. Nowadays, more and more people use almost entirely low energy light bulbs. And we've moved from 60 watt or 100 watt light bulbs to most light bulbs being only 10 watts. And so there's been a massive reduction in the electricity needed for lighting throughout the country. But also there's been a big push to more energy efficient devices. So we've gone from very large cathode ray tube TVs to flat screen TVs. We've got energy efficient washing machines, energy efficient dryers. So the upshot is that the peak demand in the UK was about 380,000 gigawatt hours in 2005, and now in about 2020 it's down to about 300,000. So potentially, there's 80,000 gigawatt hours of electricity that we used to supply that presumably we could still supply if people start to buy lots of electric cars. But the other thing to point out is we're not suddenly going to go overnight from 30 million conventional cars to 30 million electric cars. That transition is going to take 15 to 20 years, and so the demand for electricity for electric cars is going to come in gradually, and hopefully it will be planned. So more power stations are planned, and it's a case of matching the supply and demand of these things. But I don't think electricity supply at the moment is a particular issue for electric car uptake, certainly in the UK. And finally, in terms of UK electricity production, I'd just like to look at this slide here. And this shows how the change of fuel used to generate electricity has changed over time. So really from the 1950s right through up until the late 90s, early 2000s, a lot of electricity in the UK was generated from coal. Even in 2014, more than 30% was generated from coal. But that's a substantial reduction from the 60s and 70s, when sort of like anything from 50 to 80% was coal. So later, in 2019, there's only 5% from coal. So we've almost entirely eliminated coal now from the UK electricity mix. One of the reasons for that is we started using more and more gas from the mid-90s onwards, and natural gas now makes up about 35% of our electricity mix. We also have quite a substantial amount of nuclear electricity, and what we've seen in the last 10 years is quite a big increase in renewable electricity. So in 2009, you probably only talk about 2 or 3%, but that's now grown to sort of more like 15%. So we can see that over time, we've had quite a big reduction in the CO2 emissions from our electricity grid. And again, this is all data that you can have a look at if you've got time afterwards. So I'm going to move now from cars to talk about different heavier duty vehicles. So CO2 emissions from cars, as I said, is a fairly easy thing to do. We can move people over from conventional cars to electric cars. The batteries should be big enough. The challenges are making sure the cars are affordable and that there's an efficient charging system in place, and that will sort of grow as the uptake of electric cars will grow. But for some of the other transport that we use, it is going to be considerably more difficult. So if we look at trains, planes, heavy duty trucks and ships, what they do here is they look at the CO2 emissions in grams per ton kilometre. This is for freight rather than for passenger use. So what they want is how many CO2 emissions are emitted for every ton that we transport. So obviously it goes up if you transport heavier loads, and it goes up if you go for longer distances. And obviously a plane is pretty inefficient in terms of freight because it uses a lot of fuel, and it emits 1,200 grams per ton per kilometre. And effectively, most of the time we use kerosene in planes. You can't really see that going to electricity in the near future. And so what people are looking at for the future of those is looking at biofuels and kerosene made by electricity. But saying that, planes are relatively small amount of the global CO2 emissions. Are only 2.5%. If we look at trains, that's a lot easier to do because the emissions from trains are actually quite low, 25 grams per ton kilometre, so substantially less than a plane. A lot of trains also now run on electricity, so if the electricity is decarbonised, it sort of automatically becomes low carbon. And so the challenge is to move from the diesel fuel trains to increase the electricity, and people are also looking at things like hydrogen. But trains are even lower than planes, are only 0.3%. If we look at ships, ships are actually very efficient in terms of moving freight. Although a ship clearly burns a lot of fuel, because it's carrying so much weight. The CO2 emissions per ton kilometre are actually quite low. So on average, a ship is lower than a train, but in fact, for bulk shipping, the big container ships, you're down at even lower figures, 2 or 3 grams per ton kilometre. So ships are a very efficient way in terms of CO2 emissions of moving freight. At the moment, fairly low quality bunker fuel or gas oil is used, but some ships are moving to liquefied natural gas, which is a fossil fuel, but it's a fairly low carbon option. And what people are looking at for the future are they're looking at more use of LNG, they're looking at hydrogen ships, electric ships could be an option for short routes like ferries and stuff, but there's also biofuels, methanol, and people are even looking at things like nuclear reactors. So, I mean, there are things looking at here, but I mean, they're a longer term option. And then people are often surprised, but heavy duty trucks are actually about 8% of worldwide CO2 emissions. So after cars, trucks are something to focus on. And trucks are fairly efficient at moving freight, but they're not as good as ships or trains. Currently, a lot of countries, trucks are running on diesel. Some countries, they have LNG, liquefied natural gas, and some have CNG. But people are looking at moving over to electric, hydrogen, more LNG, more CNG, and more biofuel. But I think the point to make here is that although these options are being looked at, I think it's going to take longer to decarbonise these sectors than it is to decarbonise the passenger car fleet. So really, I just want to conclude. The main message hopefully you've got from this talk is that electric cars can result in lower CO2 emissions compared to conventional cars, providing you're in a country where the electricity grid has a high proportion of low carbon electricity generation. So in the UK, we're in such a country. Over 50% of our electricity is now low carbon, which I call wind, solar, nuclear, and much of the remainder is gas, which is a substantially lower carbon content than coal or oil. And the challenge that people are looking at now is to how are we going to decarbonise these harder transport sectors, such as heavy duty trucks, ships, planes, where electrification is not as straightforward. So there's been a lot of information in this talk. I mean, there's quite a lot of things you can read after the talk to get more information. I would certainly recommend the book at the top. It's probably about 15 years old now, this book, Sustainable Energy Without the Hot Air, and some of the numbers in the book might be getting out of date, but the principles behind how he does the calculations of how much energy is produced and what the CO2 emissions are makes this a really good read. And back in 2007, Julia King was asked by the government to do a review of how to decarbonise the passenger car sector, and the King review of low carbon cars really recommended moving to electric cars and formed the basis for where the direction the UK government was going in. There's some useful websites where you can look at what the outlook is of electric cars by Bloomberg and McKinsey, and there's a recent Shell Sky scenario where they tried to look at what you needed to do to actually make sure that the temperature rise from global warming didn't go above 1.5 degrees C. So they tried to estimate how many electric cars you'd need, what changes you'd need to make to actually do that, which is quite an interesting read. And then I've recently written a paper on vehicle electrification, and some of the numbers that I've talked about here, some of those are in that paper. So so that might be worth a read. So I'll finish there, and hopefully you found the talk interesting, and I'm quite happy to answer any questions.
Thank you very much, Ian. That was very interesting. If people didn't get a chance to scribble those internet links down, don't fret. The presentation will be available soon on the IMechE website with the other videos and presentations that we've held. It's interesting. Ian says that the lighting has resulted in such a drop in energy consumption. We're going through a process where I work just now, where we're replacing around about 150 light units, each previously rated at 240 watts with 60 watt LEDs, and we're getting a lot more light out of that. So it's a really good process, but I am still concerned with the when we turn all the nuclear power stations off, with the new housing being forced to abandon gas boilers and gas cookers, whether we'll still have enough energy generation through efficient means. Is that, have you taken that into consideration in your numbers, Ian?
Not really. I mean, my understanding is, although there are some current nuclear power stations that are planned to be decommissioned, I think the government now is talking about getting new ones built. So I think nuclear is probably going to be part of the solution. I think the trouble with wind and solar is if you have cloudy days or still days, the emissions can stop. The generation of electricity can stop. So you need to have some sort of backup. You don't want to have a gap between supply and demand. So I suspect nuclear will carry on being part of the solution. And in fact, one of the reasons the UK is got a low carbon electricity system is that we do have nuclear. I mean, Germany, quite ironically, given how many cars and car manufacturers are there, their CO2 footprint for electricity in Germany is much worse than the UK's, because they suddenly switched off all their nuclear power stations after the tsunami in Japan. So even though they're not surrounded by water, they somehow decided they'd switch off all the nuclear power stations, and so they actually have a lot more coal-fired power stations generating their electricity than we do in the UK. So the conclusions I've given here have really been specific to the UK, and you've got to look at your country to see what the CO2 emissions are of your electricity supply, to see what the potential is for reducing CO2 emissions when you move to electric cars. But I think planning for a sufficient supply and demand of the electricity system is obviously going to be crucial going forward.
Right. Thank you. Oliver asked, in your calculations, did you recognise the CO2 emissions during the diesel or petrol refining process? Is that included? And adding to that, I look at pictures of oil wells and in the sea, engulfing clouds of burning fumes which have been lost and wasted. Is that taken into account with the efficiency figures that you've mentioned?
I think if I go back to one of my slides, in one of the papers that I mentioned, the CO2 emissions from fuel production were quoted, and they were about the same as the contribution from the vehicle manufacturer. So they were quite a bit lower than the simple burning of the fuel. So there was an effect there. I think you're right. I mean, you can get, well, you obviously use energy to make and extract oil and gas, and in some fields you burn gas, so you sort of waste it. But I think the volumes of oil and gas produced are so enormous, the figures are quite low compared to simply burning the fuel. So I think you can include those figures, but I don't think it makes a massive difference to your conclusions.
Thank you. Someone asking you to define what e-kerosene is in difference probably to normal kerosene.
Yeah, so maybe the discussion is, this is probably less common in the UK than it is in Germany, but in Germany there is a lot of discussion about e-fuels. So the idea is they want to take CO2 from industrial plants or from anywhere else it's generated and use electricity to convert the CO2 and water into hydrocarbons, and they call these things e-fuels. And a lot of German car manufacturers see this as really attractive because they can carry on making conventional engines and use these e-fuels. And the argument is the CO2 they've made to make the fuel, you then burn it off when you burn the fuel, but then you recover the CO2 and make the fuel again. So they sort of say it's sort of renewable. But anyway, whether you agree it's renewable or not, there's this lot of interest that you can potentially extract CO2 from the atmosphere, combine it with water and electricity, and make a hydrocarbon fuel. And so the idea is that you would make kerosene by that process. I think the problem is it is going to be very, very expensive to make the fuel by that process compared to the cost of conventional kerosene. And secondly, it's highly doubtful that you could actually make enough of it to fuel the entire airline industry. And then you've got the question: is it really renewable? I think it's almost inevitable you're not going to recover all the CO2. But I mean, that's what they mean by kerosene or e-fuel, is that you can somehow make hydrocarbon fuels from CO2 and water with electricity. And like I say, the debate is, if you have this electricity and it's from a renewable source, do you want to do that, or is it better just to put the energy into a battery straight away? Because you're probably able to travel a lot further on the battery than you would. You're going to lose energy to actually make the fuel in the first place, and so it's a less efficient route. But for things like planes, that might be the only way to go if you can't use batteries, because on a plane you'd need an enormous battery, which is too heavy. So, and also it's a bit hypothetical, some of these discussions, because I'm not sure that there is actually a process yet, an efficient process for actually making this e-fuel. So a lot of people are talking about it, but I'm not sure there's a commercial process in place by which these e-fuels can be made economically. But I mean, that's what they mean by e-fuel in general.
Thank you. Do you think enough investment going on in the heavy goods sectors? Do you think there needs to be more government incentives for that to happen? What's your feeling?
Yeah,
that's my question.
That's a good question. So, I mean, if you're talking about heavy duty trucks, long haul, then there aren't a lot of options. You could go to higher biofuel content, which is what the UK government is doing. They're trying to get to 10% biofuel content as opposed to 5%. Or you could move to liquefied natural gas as a fuel. But the long haul trucks it's not going to be easy to electrify those. And people are talking about hydrogen. But I think the challenge with both gas and hydrogen is to make the trucks affordable, because I think they can be quite expensive to buy, and hydrogen particularly be expensive to buy the truck and expensive to run. So there are lots of people looking at lots of options, but I think you're right, the investment is probably lagging behind what it has been on cars, and it's probably I think that the focus on trucks will come once they start to see a substantial move to electric cars. I think they're trying to do one at a time, effectively.
Well, thank you. Aidan is looking at the tables, and he's identified that it looks more efficient for two people to travel in an electric car than to travel on bikes if you're looking at CO2 emissions. It looks a bit odd. You feel that's correct? And
yeah. So if I go back to that table, I was looking at how much energy you need to cycle 100 kilometers. I think in practice, people who go on a bike, they're not going to go 100 kilometers. They're going to go like 5 kilometers to the shops. So the energy you need to go 5 kilometers to the shops is obviously a 20th of the energy you need to. It's probably going. Yeah, so it's 20 times less than the energy you need to cycle 100 kilometers. So I think you're right. If you, I mean, it's partly a consequence of the low CO2 emissions of the UK electricity system, and I mean, you do need quite a bit of energy to cycle, and if you're cycling 100 kilometres, you need quite a lot of energy. You've got to put that back in. So I think the figures are right. It's just, I think, in practice, people who cycle as a mode of transport are not going to cycle 100 kilometres. They're going to cycle 5 kilometres to the shops and back, and that'll be about it. So I think that the numbers are definitely correct, because you can simply look up what the energy is needed to go 100 kilometres in an electric car. You can estimate the energy to go 100 kilometres on a bike, and you can see what the CO2 emissions are. So the numbers are definitely correct. It's just, I think you're comparing apples and pears here. The bike is going to be used for short distance transport in practice.
Thank you. Some ideas from the past of a perfect future was generation for atomic power station, creating lovely clean electrical power, and at the same time being used at high temperatures using sublimation to generate hydrogen to power the vehicles. Is that a past idea? Have we gone on from that? Is that unattainable now? And
yeah,
that was my question.
Okay.
And following on from that, someone else has asked, can you see a genuine application for hydrogen that is a better alternative to pure EV? It seems that much of the general public are in the belief that hydrogen is the better alternative for environment for long-term future, certainly of heavy goods vehicles, than EV. But your article seems to dismiss that as not been an option.
Well, I think it is an option. I think I just put the figures in for how hydrogen is generated today, which is mainly by steam reforming. And so most hydrogen that is made today is not made from renewable electricity, and it's made from a steam reforming process. So I think there are hydrogen prototype plants being developed where they use different processes to make hydrogen, which might be more energy efficient than CO2. That might be better from a CO2 point of view from the current way hydrogen is made. But at the moment, those plants aren't available, so you can't really put in the numbers for those plants because we don't have them yet. But I mean, if you can make hydrogen in a more efficient way, it could become more of an option. I mean, I've not heard about people combining the steam from a nuclear power station to make hydrogen, but I think people are talking about using renewable energy to make hydrogen, which would be a lot more attractive than the way it's made at the moment. So hydrogen is probably an option, but I think the cost of hydrogen is still going to be an issue, and there is a debate going on whether hydrogen should be used for cars or whether it should be restricted to heavy duty trucks and ships and planes. So I don't think hydrogen is a very sensible option for passenger cars, but it might well be a good solution for heavier duty modes of transport. And also, I mean, if someone comes up with a good way of making it, which makes it cheap and is less CO2 intensive, then that will change the outlook for hydrogen.
Thank you. There was a question whether the regenerative braking of which is often employed in electric vehicles was considered in your calculations. You seem to be comparing power required has been 26 kilowatts per journey on both applications, where in actual fact you'd probably require less than that with regenerative braking.
What I was doing in that table was simply using the manufacturer's own energy estimates for going 100 kilometers. So when you buy an electric car, the manufacturer should tell you this is how much energy in kilowatt hours it takes to go 100 kilometers on a standard test cycle. If you drive on a journey where there's lots of downhills or you're coasting a lot, you could well get away with less energy to go that distance because of the regenerative braking, but it depends on the journey. So on average, the OEM manufacturer figures should be right, but you could get a more energy efficient journey if you had a lot of regenerative braking on that journey. If you see what I mean.
Yeah, I think so. So thank you. Well, unless there are any more last-minute questions, I think that probably concludes the meeting for tonight. I would like to thank Ian. Very interesting meeting. Something very close to my heart. I work in a specialist vehicle company who is currently working on a new EV project for hearses and limousine applications. So it's something that I'm very close to, and I was debating the other day whether hydrogen was the way to go forward or not, and it seems a confirmation from what Ian said that we should stick with electric vehicles. That is the way forward. We have a couple of last-minute questions, Ian, if you're okay to answer them.
Yeah.
Which industry do you see will have the focus in the next 5 years? Now, I think that's probably beyond transport. I think he's looking at other industries which could benefit from the investigation of CO2 reduction.
Yeah. So I think the main route the UK government is taking to reduce CO2 emissions is to try and electrify everything. So if you can decarbonise the electricity system and electrify everything, you can potentially get the CO2 reductions down. So that's relatively straightforward to do with the cars by moving to electric cars. It's going to be less easy to do for other sectors. So, but I mean, what they talk about with heating is they're talking about replacing gas boilers with either hydrogen boilers or heat pumps, and the heat pumps effectively generate electricity. So I mean, I think, and if you go to an electric heating system and you've got a decarbonised electricity supply, you'll have lower CO2 emissions. But the downside is that the electricity cost per kilowatt hour is quite a lot higher than the gas price per kilowatt hour. So your heating bills would go up quite a bit if you moved totally electric. So there are quite a lot of difficult discussions going on, and trying to work out what to do with the UK housing stock and moving them to lower carbon heating is going to take quite a while to sort out. In terms of the heavy duty vehicles like ships and planes and trucks, I think the UK government is having similar discussions that are going on in other countries. So I think that's a more international discussion about what way to go. I mean, the UK government can't simply solve the problem of planes on its own. And in terms of heavy duty trucks, you've already got a lot more of this start-stop trucking delivery. So the 7-ton trucks doing Amazon deliveries. In fact, those probably could even move to electric. It's the long-haul trucks which are more of an issue, and the ships. And people on shipping, people are looking at things like ammonia and methanol as instead of hydrogen. So potentially those are fuels that could be lower CO2 before a hydrogen option becomes available. So I think there's lots of discussions going on about all of these sectors, because to meet net zero by 2050 or whenever we've committed to, you've got to look at every single sector. But I think they're trying to do the easier to meet ones first. So it's going to take a while, I think, to sort everything out.
Thank you. By the way, Amazon is already heavily investing in an EV vehicle manufacturer.
Okay.
A bit of inside information. Right, again, thank you very much for that interesting presentation, Ian. I would like to let the attendees know of a few more events that the Lancashire panel of the IMechE are arranging in the near future. On the 23rd of February, we have Rolls-Royce Small Modular Reactors, which is a webinar, similar presentation to tonight. On Wednesday, the 30th of March, we are hoping to have a face-to-face talk and tour around AMRC Salisbury. AMRC is a very interesting forward development organisation looking at advanced methods of manufacturing. I was lucky enough to look around there myself recently. It's well worth a visit. So that's Wednesday the 30th of March. And the next one after that is Wednesday the 27th of April, where we're arranging a visit to Bolton Steam Museum, where all the steam engines, etc., will be working, and there'll be experienced staff to talk to us about the equipment that's working. So we've got 3 events, COVID permitting. But thank you very much for your attendance, and goodbye. Thank you.
Thanks. Bye.
Bye-bye.